Alright guys, so today we are going to be discussing linear regression, which is the most simple machine learning model that I could think of personally. It's also one of the most useful machine learning models because it requires very little processing power and can be applied in a wide variety of applications. So those of you who have taken statistics, you may be familiar with this model. In that case, you can just skip this video and we will get to the coding. So in short, linear regression is a way to tell the relationship between an x and a y variable. So what we're going to have is we're going to have a bunch of data points on the x and y axis, and what linear regression is going to try to do is find a linear line, a linear relationship between the x and y values. So then we can predict other x and y values that aren't actually plotted. So what does this look like exactly? Well, it looks like this. So right here, the green squares that you see, those represent the different data points and they're plotted on the x and y plane. And what linear regression is trying to do is it's trying to make a straight line. It's trying to make a straight line that minimizes the error. Now the error right here is represented by this red line right here. What you see it is it's y hat, meaning the predicted y value, which is the line right here, minus y, which is the actual y value, and then that's in absolute value bars. So what this line is doing is it's slowly adjusting itself to find the correct slope and the correct intercept. So we have w naught is the intercept. It's trying to find the correct slope and the correct intercept that makes the total error as small as possible. That makes it so that each of these red lines are as short as possible and that the line is as most representative of the data as possible. So once it creates this, what it's going to do is now you can predict values. So for instance, we can say in our example that the y right here, this represents the sales price of a house, and the x right here represents the square footage. So here are all of the houses plotted with their square footage and their sales price, and you can see the house with the biggest square footage also has the biggest sale price, and the house with the smallest square footage has almost the smallest sale price. So from there, when it creates the line, what you can do is you can predict. You can say, okay, well, if there's a house right here with this amount of square footage, we can predict about what the sale price should be. So that is what's useful about linear regression, is that you can make simple predictions like that. And you can apply it to literally any linear relationship you can think of. I'm just using the example of housing prices because that's what we're going to be working on in the next video. So the math behind this equation is actually quite simple. It does look a little bit intimidating, but all you're really right here trying to get is you're trying to optimize for the population y-intercept, the population slope coefficient, and then the internet independent variable with the error. And you're trying to minimize the error as much as possible so that it makes the line of best fit. Now with that being said, sometimes you can have your model overfit or underfit. And this is something that applies to most, pretty much all algorithms have a problem with overfitting or underfitting when you're running your models. So this is good to keep in mind for the rest of the course and also when you're doing machine learning on your own.
In fact, overfitting is such a common problem that Udacity did a parody of Michael Jackson's Thriller about it.
You overfit it, spit it out. Mistakes you shouldn't make, evaluate the testing set. You overfit it, quit it now. You'll need another way or you'll regret it. Get it, no doubt.
So an example of an underfitted model would be right here. So here we have the x and y data, and you can see this linear relationship. You can kind of see where the model's getting that from, but it doesn't accurately describe the data because you have stuff over here, stuff over here, stuff over here. Now a good fit for this data would be something like this. So this isn't linear, this is logistic regression, but you can see it fits the data much better. So underfitting's here, and then overfitting is when the model is too good. When it is so accurate at predicting that what ends up happening is it doesn't actually truly describe the data. So this can become a problem because even though on the training data this works perfectly, on outside data, on new data, this model isn't going to work as well as the good fit model right here. So that's why you want to avoid overfitting or underfitting your model, because what can end up happening is that when your model gets new data, then there are going to be some issues. Basically, in order to find out if your model is overfitting or underfitting, you have to look at the loss. And the loss is something that Keras is going to print out for you while you're training. Basically what it is the punishment that the neural network or the model receives for getting something wrong. So if the loss is very, very low, that means that the model is very, very accurate on the training data. And this is actually bad. You don't want your loss to be too low, because if your loss is too low, then it's going to look like the overfitted example right here, where it perfectly matches the data but doesn't actually match the data as a whole when you're put into account new data. Alright guys, so by now you all know about linear regression and a little bit how it works. Now in this video what we're going to be doing is we're going to be performing linear regression on some data that I have. And this data is from the Iowa housing prices market, and this is real data. I edited it a little bit so that it could be simpler for our purposes for beginners. Basically what we're going to do is we're going to make a model that'll predict, based on the square feet, what the price of the house is going to be. So we have 1,460 entries of this data that we are going to be training on, and we're going to make a model that's going to be able to predict, based on square feet, the sales price of a house. And this is real data too, which is really cool. So in order to do that, the first thing that we're going to do is import our necessary libraries. So we're going to import Keras, which is going to be our machine learning library. We're going to import NumPy as NP. This is going to do some math for us later. We're also going to import pandas as PD. This is going to help us read in our data. And then we're finally going to import matplotlib.pyplot as plt, and this is going to let us graph our linear regression model and see what our data looks like, which is really cool. So we're going to shift enter to run that cell and create a new cell. Next, what we need to do is we need to mount our drive so that we can get access to the data. Again, like I said before, you can get access to the data by going on my GitHub and then getting the link directly, or you can download it, save it to your own drive, and do it like the way that I'm about to do it now. Or you can upload it to your runtime right here on the side. The choice is really up to you, but for this example, I'm going to mount the drive, and I'm going to run this. It looks like my drive is already mounted, so all I have to do now is just put in the CSV to our file. So we're going to say df for data frame is going to equal to pd, which is pandas.read CSV. And by the way, if you don't know, CSV stands for comma separated file. So it's basically like an Excel spreadsheet if you think of it. We're going to do the location of the file, which I will get right here by saying copy path. Then I'll paste it into here. I can get rid of the content part. It'll work just the same. And we'll run that. And it looks like our CSV was imported to the file just fine. So that's good. Next, what we need to do is we need to set the X and the Y variables. So if I open up our housing prices CSV again, you'll see the X right here is going to be the square feet, this column right here, and the Y is going to be the sales price, this column right here. So we're going to say square feet is equal to df, which is what we set up here. We're going to do double square brackets and then square feet, which is the name of the column right here. And we're going to say dot values And then we're going to do the same thing for sale price. So sale price is going to be equal to df double square brackets sale price dot values. All right, sweet. So we'll run that sucker. And now it's time to actually build the model. So the first thing that we're going to do is create the model by setting model equal to Keras dot sequential, showing that we're building a sequential model. And then we're going to add just one layer to the model. So model dot add, we're going to add from Keras dot layers dot dense, and you can learn more about what a dense layer is in the Keras documentation. But basically we're going to build the simplest model possible in Keras for linear regression. So now a really cool thing about Colab, or also Jupyter Notebook has this too, is that if you press the tab key, what it'll do is it'll pull up a little box right here that'll show you the documentation. So for instance, if you forget all the parameters that need to go into a function that you're using, for example, you can easily just pull this up and then it'll show you everything that you need to know. So from reading this, we can see that our dense needs 1, because we're just doing 1 neuron, and we need it to have an input shape equal to 1 comma, and nothing goes in here, because again what we're doing is we're feeding in one value and then it's giving us one value back. Okay, so we have the model created. Now we need to compile the model. So model.compile, and we're going to use optimizers. Now the optimizer is going to be that algorithm, that little function that's going to minimize the loss of the function. It's going to minimize the error. So if you think back to last video where we had the red lines, that's basically what we're going to be doing, is we're going to be inputting the correct algorithm that's going to minimize the amount of red lines that are shown on the graph. So we're going to do keras.optimizers.atom, and basically atom is generally considered to be the best optimizer, or one of the best optimizers. Most of them are going to work pretty similarly in this example, just because we have such a simple network and such a small amount of training data, but atom generally works the fastest and the most accurate. And then inside of the parentheses here, we're going to set the learning rate, which is LR, and we're going to have that equal to 1. Now basically what the learning rate is going to say is it's going to say how fast are we going through, are we going to try to optimize, basically how big are the jumps going to be when we're adjusting our model. And so a really small learning rate where it's going like this is going to take a longer to reach the optimum line, whereas a big learning rate is going to jump down, and potentially you could get it way off, but it will hit it faster most of the time. It'll just be a little bit less accurate. Because we don't have a lot of data, I chose a larger learning rate. Usually you want the learning rate to be much, much smaller. But anyways, and then finally we're going to do mean squared error. And basically what this means is that the error that we're calculating isn't just the error where it's y hat, the predicted y, minus what the actual y is. What it's actually going to be is it's going to be that squared. So there aren't going to be any absolute value bars if you think back to the picture that we had in the last video, and feel free to go back if you don't remember, but it's going to square it. So instead it's going to be like a red box that is going to be trying to optimize for. So any error is going to be squared, not just doubled, but squared. And then the atom optimizer is going to try to minimize that as much as possible. Hopefully that makes sense. If that doesn't make sense, this is kind of my first time explaining this. Please leave a comment down below, and then I'll try to edit this video later. So finally, well, let me close out of our data. Finally, what we're going to do is we're going to fit the model, which is basically training the model. So model.fit, we need to fit, if you open up the documentation here, the x, which is square feet. We're going to fit it to the y, which is sale price. And then also we need to count the number of epochs. So that's EPOCH. So epochs is going to equal to 30. Now basically what an epoch is it's how many times you're going to run through the data. So once the neural network runs through every single data point, which is about 1460 I believe, what it's going to do is it's going to run over that same data again and keep on optimizing, and it's going to do that 30 times. So generally the larger your data set is, the less amount of epochs that you want to have. But since our data set is relatively small, and because we don't have to worry too much about computational power because we're on a cloud GPU and our model's pretty basic, we're going to have a higher number of epochs, which is 30. So it's going to run through the data 30 times instead of just one time. And then finally we'll have the batch size, which is how many data points are going into the network at a time. And if this is too high, what can happen sometimes is that the model will crash. So we want to make sure that this is a little bit lower, so 10 is fine for our purposes. I find generally that the batch size doesn't matter too much in terms of the efficiency of the model. Okay, so we have the model created. Now it's time to train it by running Shift-Enter. And you'll see right here, we can see the loss that it's calculating right here. And we've gone through all 30 epochs relatively quickly. So now what we got to do is we got to plot our results and see how well the model did. So we're going to do df.plot, and remember df is our data set, and we imported matplotlib as plt right there. So df.plot. Alright, so the kind of plot is going to be a scatter plot. The x is going to be equal to the square feet. The y is going to be equal to the sale price. And we'll just make a title for it. So the title will be equal to housing prices and square footage of Iowa homes. And you don't have to include a title if you don't want to. It's just generally if you want to save this to a PNG or screenshot it or whatever, you might want the graph to look a little bit nice to show off your findings. Okay, and now y underscore pred, we're going to set that equal to the line, the linear regression line that we just created by training the model. So this is going to be equal to model.predict the square feet. So again, what this is doing is it's saying, okay, so the model is going to predict the square feet that is actually in our data set, and then it's going to plot that. And so that's what ypred is. It's basically the y hat value, if you think back to that picture when we talked about linear regression. And then all we have to do now is just plot this. So we're going to do plt.plot. We're going to plot square feet as the x. Y pred is going to be the y, the predicted y value. And the color of it is going to be red so that we can see it. Because default is going to be blue and you're not going to be able to see it very well. So we'll run that. And you see right here, this red line is the regression line that we trained. And then these are all of the different data point values. So it seems to be fitting the data pretty well. However, there is a lot of variance in the data. Now, if we want to predict a new data set, what we're going to do is create a new variable. So I'll just say new SF for square footage. And let's set it, let's say, equal to 2,000 square feet, which is pretty large. And then what we're going to do is we're going to print model.predict, and then inside of here, inside brackets, new SF and you'll see, based on the model, the predicted price for a home that is 2,000 square feet is going to be $239,000 to buy. So that's pretty much it, guys. You just successfully created your first machine learning model. Let me know if you guys used this linear regression for anything else other than Iowa homes, and I will see you in the next video. Sweet.
Thank you guys so much for making it to the end of this video. As always, if you enjoyed it, make sure to hit that like button. Also, if you have any questions, comments, or concerns about what we did in this video, please leave them down below. Now, if I could have just one more minute of your time, I would like to tell you about a service that I've been using for over a year now called Scribd. Now, just as a side note, Scribd did not sponsor me to make this video. I just wanted to tell you about it. Put simply, Scribd is a lot like Audible, except for instead of being $15 a month, it's only $9, and instead of only having 2 audiobooks per month, you get an unlimited access to a plethora of audiobooks, ebooks, documents, and even sheet music and magazines. So for me, this was obviously a no-brainer, and right now, if you use the link in the description, you get 60 days free of Scribd, and I get 1 month if you sign up using my link. So that's why Scribd didn't officially sponsor this video. I'm just telling you about it so that I can get some free months, and I can continue learning, and you can also continue learning with your 60-day free trial. So thank you guys so much for making it to the end of this video, and I'll see you in the next one. Peace.